Acids, reaction of carbonic acid and two equivalents of OH minus or hydroxide ion. Well, if I'm going to react two equivalents of hydroxide ion, I can imagine both of these hydrogens are going to be removed. In that case, then the organic product is going to be the ion produced with both of these oxygens being negative. Acids, reaction of trimethylamine and ethanoic acid. So if we're going to predict the products of the acid-base reaction of this, then what we need to realize is this is the hydrogen that will be abstracted by the lone pair of this nitrogen. Therefore, we're going to draw the molecules on the canvas. So what I need to do is first, I like to start with my starting material. There are my reactants, so now I can react them. Now I'm going to take off this hydrogen, and the way that I'm going to do that easily is pressing the negative sign, and that makes the that makes the oxygen a negative, and then I'm going to take a hydrogen and bond it to my nitrogen, which makes him positive. Draw the structure, the predominant form of this molecule at pH 10. Well, at pH 10, it hasn't lost a hydrogen. We need to be at a pH equivalent to the pKa in order to lose that hydrogen. Therefore, the predominant form at a pH of 10 is just what is given to us there. So this is how I draw the molecule, and then I press my positive in order to make nitrogen positive, and that's the form of the molecule. Number 8, acidity of alcohols and phenols, ethanol and ethoxide ion. So which side of the equilibrium will this figure favor? Going to Appendix 1 in your book, and I'm actually looking on page A2, I have ethanol and water, and they're actually very close to one another. So ethanol is acting as the acid here, and it has a pKa value of 16. Remember, my arrow is going to point towards the larger pKa value. And over here, I have water as my acid, and it has a pKa value of 15.7. Therefore, I will favor reactants in this particular case. Acidity, we're going to rank these particular compounds from most basic to least basic. Now remember, most basic is least acidic. If it's easier for you to think in terms of acidity, then substitute most basic for least acidic and least basic most acidic. So that's what's easier for me. So I can take the amide, and that's going to be the most acidic because he has hydrogens to lose. Then comes the piperidine, and then 2266 tetramethylpiperidine. Acidity, we're going to rank these compounds from most acidic to least acidic. Now you need to remember both the size of the atom and electronegativity. So in this case, we have the size of the atom and the electronegativity to take into consideration. So this should be my order. Number 11, we're going to rank these compounds from most acidic to least acidic. So we're looking at the hydrogens attached here to the methyl group. And here, the most acidic is actually going to be this one here because the fluorine is going to draw these electrons down, followed then by the chlorine and then that one. Acidity. Rank the compounds in order of acidity too. Well, this can be misleading because, especially if you don't read this part here. Part A, it wants you to rank these bases in order of basicity, not acidity. Now, I know that sodium hydroxide is going to be the strongest base out of the bunch because sodium hydroxide is an ionic compound and it dissociates into sodium and hydroxide. Now, the stronger the base, the weaker the acid. So if it's easier for you to compare pKa values, you go right ahead. Now, the weaker the base, then the stronger the acid. And then I know that ethanol actually has a pKa value of somewhere around 16. Therefore, that's probably going to be my weakest base because it's my strongest acid. In that case, then we're comparing between these two compounds, and I'm just going to drop them here just to look at them. Between these two compounds, what we have is a carbonyl. And that carbonyl is actually going to stabilize the conjugate base. Therefore, that's a stronger acid than this one, indicating that that's our order of basicity.